Here is a question that sounds trivial. What time is it? In a distributed system, this question has a surprisingly complicated answer. Every machine on the network has its own clock, an actual hardware device, usually a quartz crystal oscillator. These clocks are not perfectly accurate. Each machine has its own notion of time, which may be slightly faster or slightly slower than other machines. It is possible to synchronize clocks using the Network Time Protocol, NTP, which allows a computer's clock to be adjusted according to the time reported by a group of NTP servers, which in turn get their time from more accurate sources such as GPS receivers. But here is the critical distinction the book makes, and it is one that engineers routinely get wrong. Modern computers have not one but two fundamentally different kinds of clocks, and they serve completely different purposes. The first is the time-of-day clock. This is what you intuitively think of as a clock. It returns the current date and time according to the calendar, also called wall clock time. In Java, this is system.currentTime millis. In Linux, this is clock_getTime, clock_realtime. Time-of-day clocks are synchronized with NTP. That sounds good, but here is the dangerous property. If the local clock is too far ahead of the NTP server, it may be forcibly reset and jump backward in time. Backwards. Your timestamps can go back in time. This makes time-of-day clocks unsuitable for measuring elapsed time. The second is the monotonic clock. This is suitable for measuring a duration, a time interval. In Java, this is system.nanotime. In Linux, this is clock_getTime, clock_monotonic. The name comes from the guarantee that it always moves forward, it will never jump backward. But here is the trade-off: the absolute value of a monotonic clock is meaningless. It might be the number of nanoseconds since the computer started. You cannot compare monotonic clock values from two different computers because they don't mean the same thing. The rule is simple once you understand it: use time-of-day clocks for timestamps on events. Use monotonic clocks for measuring how much time has elapsed. Mixing them up is a source of subtle, hard-to-diagnose bugs. So you're using NTP synchronized time-of-day clocks. How accurate are they? The numbers may surprise you. The quartz clock in a computer drifts, it runs faster or slower than it should. Google's own servers are assumed to have a clock drift of 200 parts per million. Let's do the math. 200 parts per million means 200 microseconds per second. If a server is synchronized with NTP every 30 seconds, that's a potential drift of 6 milliseconds between synchronizations. If the server syncs only once a day, the potential drift grows to 17 seconds. 17 seconds of clock error on a server that syncs once a day, not once a year, once a day. NTP synchronization itself has a minimum error of 35 milliseconds achievable under good conditions. On a congested network, NTP errors spike to around 100 milliseconds or more. Some NTP servers are misconfigured and report time that is off by hours. Leap seconds result in a minute that is 59 or 61 seconds long, which has crashed large systems. In virtual machines, the hardware clock is virtualized. When a CPU core is shared between VMs, each VM is paused for tens of milliseconds while another VM runs. Now here is where clocks intersect with another problem: process pauses. A node in a distributed system can be paused for a significant length of time at any moment, even in the middle of executing code. The Java virtual machine has a garbage collector that occasionally stops all running threads to collect memory. These stop-the-world GC pauses have been known to last for several minutes. Not milliseconds, minutes. In virtualized environments, a VM can be suspended entirely and resumed later for an arbitrary length of time. The OS context switches to another thread. If the application does synchronous disk I/O, the thread waits for the disk. If the operating system swaps memory to disk paging, the thread waits for that. Even a Unix 6-stop signal, sent accidentally by an operations engineer, pauses all activity. The danger: a node can be declared dead by its peers while it is simply paused. It wakes up, checks its clock, sees that only a few milliseconds have passed, and happily continues acting as if it is still the leader, unaware that it was already dethroned. Here is a concrete example of how clock skew causes real data loss. Imagine a database using multi-leader replication. Client A writes the value x equals 1 on node 1. Node 1 records this write with a timestamp of 42.004 seconds. That write is replicated to node 3. Client B then increments x on node 3, creating x equals 2, which is timestamped at 42.003 seconds, because node 3's clock is slightly behind node 1's clock. The skew is less than 3 milliseconds, which is actually better than you'd expect in practice. Now both writes are replicated to node 2. Node 2 sees 2 writes. It uses the last write wins strategy. The write with the higher timestamp is the more recent one. The write of x equals 1 has timestamp 42.004. The right of x equals 2 as timestamp 42.003. Node 2 incorrectly concludes that x equals 1 is the more recent value and drops the increment. Client B's operation is silently lost. No error is reported. This conflict resolution strategy, called last write wins or LWW, is widely used in Cassandra and RIAC. And with clock skew of just a few milliseconds, it silently discards data. Most systems do not expose the uncertainty in their clock readings. When you call clock_getTime, you get a number. You don't know if that number is accurate to 5 milliseconds or 5 seconds. Google addressed this in Spanner, their globally distributed database, with an API called TrueTime. When you ask TrueTime for the current time, it doesn't return a single point in time. It returns two values, earliest and latest, the earliest possible and latest possible current timestamp. The width of that interval is the uncertainty in the clock measurement. If the intervals for two events don't overlap, you know their order with certainty. If they overlap, you don't. To keep the uncertainty small, typically within 7 milliseconds, Google deploys a GPS receiver or atomic clock in each data center. They literally use atomic clocks so their database can safely use timestamps to order distributed transactions. The lesson: ordering events across distributed nodes using timestamps requires either atomic clocks and careful engineering, or abandoning timestamps entirely in favor of logical clocks, counters that track causal relationships rather than wall clock time.